Everybody, welcome to the FEA webinar series, session 2. We'll be focusing on Ansys Mechanical pre-processing and solving today. Please do ask questions during the session if there's any. Alternatively, you can ask your question in the chat and we'll try and get back to you during the session. Otherwise, we'll have a Q&A at the end. So, Jean-Marie, I'll hand over to you now, then you can just start with the presentation.
Okay, great. Thank you, Laura. So let me just turn on my camera quickly to introduce myself. For those who are perhaps new, so my name is Jean-Marie and I work for QFinsoft, and I specialize in finite element analysis, especially on the mechanical side. So as Laura has mentioned, last week we looked more at space claim and the geometry preparation and optimization that we would typically do for a finite element analysis. And this week we will be focusing on Ansys Mechanical, which I will get to just now. So let me start sharing my screen. So there we go. I'm just quickly going to go through the background of the analysis that we'll be doing, and certain assumptions that are made, as well as some of the loading conditions for this case. Okay. So again, today is session 2, focusing on Ansys Mechanical, pre-processing and solving. So this entails a few things from meshing to applying the correct boundary conditions and loading conditions, etc., as well as defining contact between bodies. We will be covering some additional things as well. So obviously we'll be assigning some material properties to our parts. Apply contact, as I've mentioned. We will post-process some of the results that we would typically look at. And then we will also be determining the harmonic response of the chair to a rocking back and forth motion that I've estimated. So from those results, we will use the fatigue tool to calculate damage and useful life. And then finally, we'll just create a solution combination of both the static structural and the harmonic response analysis in order to get an idea of the overall or final response of the chair. Okay, so just quickly covering how we will be constraining our model and the loads we will be applying. So I found some specifications on Google regarding the basic office ergonomic chair. So I'm speaking under correction, but these are the specifications I found and have applied. So the expected life or the warranty of this chair is meant to be 5 to 7 years for 8 hours of use a day. So this is equal to a maximum of about 20,000 hours. And if we use this as a kind of worst case scenario, this is a minimum of about 74 million seconds. So this is the life that we'd want out of this chair if you had to rock it back and forth every day for 8 hours due to intense anxiety. So we will be using a design weight of 125 kilograms today, which is also given by this specification. And the alternating load that we will be applying during the harmonic response analysis will be a 200 Newton back and forth motion at half hertz frequency. So that's about 2 seconds per period of a rock back and forth. So these are just conditions that I estimated, but let's see how this will go. Okay, so then I've also just approximated the supports of the chair by simply supported beams. And I've also added a coordinate system for where I considered the center of gravity of the human would be. So I will be applying a remote mass in this case to represent the human sitting on the chair. Okay, so this is the end of my presentation. So let's just get started. I'm going to open a blank workbench session now to show you how we will set this up. And I also have a solved workbench session for the post-processing side of things afterwards. Okay, so to begin with our project schematic, I'm just going to drag and drop a static structural analysis. Then in order to do the harmonic response analysis, I need to do a modal analysis. In this case, I'm going to do a pre-stress modal analysis. So I will be determining the mode shapes of the geometry and the stress state. And then from those mode shapes, I will be determining the harmonic response to see what the stresses are due to that. And then in the end, I'll show you how to do a solution combination of the two. Okay, so when you have your workflow set up, usually I just kind of follow the workflow within Workbench. So I'll start with my engineering data. So here is the module where you will manage all your materials and your material properties. So there are a variety of different ways that you can do this. When you open engineering data, you'll see the default is set to structural steel. And if you wanted to add any additional materials, you can activate the engineering data sources button, and then it will give you a few libraries that you can actually access with some materials that are included. So in this case, I'm just going to add a aluminium alloy that I will be using for most of the support. So this is listed under general materials. And then if I click on this plus icon, it will add the material to the database that I'll be using. Then it already has structural steel included, which I'll just be using for the beams at the bottom. And then I also have an external material data file that I will be importing, which is another option if you ever happen to have a XML file. So when I import an XML file, engineering data sources need to be off. So in this case, I can just click on imports. And in this case, I will be importing this ABS plastic, which is kind of a hard plastic that I'll be using for the cushion parts. Didn't really want to use a material too low of a Young's modulus because then the distortion becomes excessive. So in this case, I will just be using a hard plastic. Okay, so if you look at this cell here, the outline of schematic A2, B2, and C2. So this means that the engineering data is linked for all of the analyses, and these materials will be available for all of this. So yeah, as I've mentioned, if it's listed here, it will be included in your mechanical application. So then I'm also just going to import the geometry from last week. I just want to make sure I'm selecting the last one. Okay, so I'm basically using the exact same geometry as I have prepared. The only thing that I've maybe added are some additional name selections just to make the scoping a bit easier today. Okay, so now I will be starting the mechanical application. So to do this, I just double-clicked on the model cell. You can also activate mechanical by double-clicking on setup, solution, or results. So all of those will take you to the mechanical application. Okay. Just waiting for it to import the geometry. And then you will see in the structure tree, once it has opened that, all the linked analyses will be listed in the structure tree accordingly. Okay, so it just takes some time for mechanical to import the geometry. And I can verify this. Usually I likely just look at my Workbench session. It says starting mechanical. And I know I must just be patient and wait. There we go. Okay. So while we wait for these parts to import, this is the mechanical interface. If you have not seen it before, we have our graphics window where we do a lot of our scoping and kind of make visual sense of our inputs. And we have the structure tree where our components are listed that are applicable to the analysis. Okay, so here we go. Just minimize this window, actually, and just close it. Okay, so this is our chair geometry that we have prepared. And you can see that all the bodies have been imported accordingly. So we have solid bodies, we have our surface bodies, and our beam elements or beam bodies. So if you look at the geometry tab, all of these are listed here. And in this case, all the solids are grouped together and all the mid-surfaces and beams are grouped together. So the first thing I'd want to do is just assign the correct material properties. And in this case, for the armrests and the cushions, I'll just be applying this ABS hard plastic. And then for these solid rods that I'm modeling, as well as this clamp, I'm going to make an aluminum alloy just for demonstration purposes. And all of the mid surfaces will be aluminum alloy, which is also part of the specification that I saw. So let me just apply that. Okay, and then finally the beams I kept as structural steel. Okay, so this will be the first way, the first thing to do, just to maybe assign your material properties. You can also do this under materials and select insert a material assignment, where you can then graphically go select the geometry you want to assign a material to. Okay, then while I'm under geometry, I'm also just going to insert my point mass to model the human. So the design weight is 125 kilograms. And I've created a name selection to scope this load. Okay, so this is just remote mass surfaces. Okay, so in this case, I also just want to make sure I'm using the right coordinate system, which is my center of gravity of the human. And it's just important to always remember to change the X, Y, and Z coordinates to 0 to ensure that the mass is actually captured at the correct location. Okay, so that is geometry and materials. Here we can also see the cross sections of the beams that were imported. So here are all the properties that are imported listed as well for you to peruse if necessary. Okay, so that is that for materials and geometry. So I'm quickly going to do the mesh, and then we'll be defining some connections between all of the different bodies, just to define the relationship. So for the mesh, since we shared a lot of the topology, the meshing is not too bad. So in this case, what I'd want to do is maybe just make the mesh a bit coarser on my seed bodies, just because I'm not really too concerned about the structural response of them. I'm very much more concerned with, the aluminium parts and the beams at the bottom, perhaps. So in this case, with the global mesh controls, which is just if you click on mesh, I usually just use adaptive sizing to no. So I changed the default for my mechanical to be no, so you can actually change that as well. And in this case, I'm just going to turn the global capture curvature set to no. So I don't want the global mesh control to capture all the tiny little curves everywhere, because this will result in too many elements that is not necessarily required for the accuracy of this analysis. So in this case, I'm just going to apply a local mesh control to these two seat cushions. And I think in this case, I'll just make it something like a 25 millimeters. So I have played around a bit before. So it takes some engineering judgment to kind of tell where you need to refine the mesh, as long as they, as I've mentioned before, are 3 elements through every thickness for a solid body. So, okay, in this case, I'm going to capture some of the curvature. So I'm changing this to yes locally for these two bodies, but I'm not going to make it this small. I think I'll try to capture a normal angle of 60 degrees and a local minimum size of about, let's make it 5 minutes. So that is just kind of the local minimum tangent radius size. It's a bit difficult to explain, but once you start playing around with these controls and create different meshes, you will get used to it a bit more. Okay, then I'm also just going to apply mesh controls to all of these aluminium bodies. So in this case, it will also just be a sizing. I think I have a named selection for the supports. Okay, there we go. So these are some of the bodies that I'm quite interested in post-processing results for. So in this case, I would like to run a bit of a finer mesh. And for the analysis that I solved, I think I inserted a size of 5 millimeters. So I'm just going to do that again. Or actually, let's make it a bit bigger. I'm going to make it 7.5 just because I'll be running the contact tool a bit later and I don't want it to take too long. Okay, then the other bodies will probably be meshed automatically. So the last piece I just need to maybe cover is these beams, but I'll just cover that in the local mesh control. Let's maybe just make it 10 for now. So in this case, I think I've captured everything that I needed to. So let's just generate the mesh and see what we get. So in some cases, when you have a lot of different shared topology in your model, it might be necessary to mesh things in a specific sequence. So if you ever just click on generate mesh and you struggle and it gives you a failed mesh, always just try also meshing the bodies individually. Okay, so here is our mesh. So as you can see, after the meshing is complete, all of the beam bodies and the shell bodies are represented with the thicknesses as well that were imported. This is also a setting that you can change if you don't want to see the thicknesses or the imported cross sections. You can toggle this thick shells and beams on and off. Then another thing I'd just like to point out is that I have also turned on this color connection kind of legend by connection. So this just shows you how your meshes are also connected and where the topology is shared. So here you can see according to the legend here. So if it's a blue edge, it's free. So if you see any blue edges, that means you'll probably get rigid body motion. If you have a red edge, it means it's supported somewhere, etc., etc. So this is quite nice to just look at, especially before you start defining your contacts, because you want to know where you need to still define bonded contacts and such. Okay, so I'm going to start with that now before I run on too much further. So let me just quickly turn off the mesh for this. Okay, so with the contacts, what I'll be doing is defining a lot of frictional contact between these two bodies, and I'll be defining beam connections for all of these bolted connections, it seems like. So I'll be making some assumptions there regarding that. And then these two bodies I'll be connecting to each other with a joint. So I'll be assuming that the lever that is attached here is actually just keeping these two bodies fixed relative to each other. And this adjustment plate here at the back, I'll also just be bonding to the associated bodies. So let's start. I usually just start from the bottom up, or not usually, but in this case I will. Okay, so the beams, I don't need to do anything. I have shared the topology there. So it says free there, but it's actually shared in the middle. So let me just, okay. Connections. Okay, so when I have my connections branch highlighted, I have all the tools associated at the top. And what I will be doing here is adding a rivelet joint between this supporting rod here and this base, because your chair is usually allowed to swivel around. So when I add a rivelet joint, it permits only rotation about the z-axis, but constrains all the translational degrees of freedom. So I'm just going to scope. We'll just use a face. There we go. And then for the remote selection, define that one. Okay, so it's accepted the input. I'm just going to keep this as rigid for now. Then I'm going to start with defining all of the contacts here. This rod, I'm assuming, or this pipe or whatever you'd like to call it, I'm assuming is kind of screwed into this base. So I'm just going to bond these two faces together. I think I have a named selection for that. So yes, these two connections. So when you do make your name selections, it's just important to kind of keep your wits about you. Oh, another thing I've not mentioned before is your connections default setting is set to automatically generate connections on import and on refresh. I'm just going to turn this off. So it actually just detects any bodies that are in close proximity to each other and then kind of at a default bonded contact. So this is all the contact regions that it has detected. Generally, I don't work with these at all. I have done that so before, and each time it's not really what I would like to define. So I prefer to define everything myself. Okay, so I'm going to start with the frictional contacts here now. So just a manual contact region frictional. So let me just start by applying my faces. I'm going to start with applying the frictional contact between the base and this base plate. Okay, now what's important when you are defining contact between surface bodies and solids or other surface bodies are the orientations of the surface bodies. So in mechanical, you always have a color code, which is the contact side in red and the target side in blue. So in this case, you can see what's happening. And what you want in this case is for the two faces, the colors to face each other, because so that will mean that the orientation of the shell body is correct as well. So in this case, you can just toggle between top, bottom, and program controlled and just make sure that it is defined correctly. So it's not advised to keep it on program controlled because sometimes the software will perhaps use the other side. Okay, so this is what you'd want to see. And okay, this is how it's defined. I'm going to add some more faces. So I have this one face selected. I'm going to add these two side faces. So you can also do that if the shell bodies have the same orientation. Okay, then I also just need to add frictional contact between the rest. So I'll do something similar for this plate over here and this plate over here. So in this case is the top. There we go. Okay, then so this covers the contact between the base and some of the plates. I now just need to define frictional contact between the plates as well. So we do have some overlapping plates as well. So I'm just going to apply frictional contact there as well. So it doesn't really matter in this case when you use shell bodies which one you make the target or which one you make the. I think what's happening now. Let me just check. I think I used the same. There we go. Okay. Let me just see if I can apply the space as well. And I just need to, I think that's fine. Top, bottom, there we go. So sometimes you'll see a question mark when you still need to define the correct orientation. So this is how I'd like to define the frictional contact between those two plates. And then finally, I'll just duplicate this one to do the same for this plate here at the back. And okay, and just change the orientation to the correct one. Okay, cool. Awesome. So we have defined the frictional contact between our base and most of our supports. So I'm going to move on to our armrests. So I also have name selections for these. Over here, I have shared the topology, so I don't need to add any contact there. I just need to add contact here. So in this case, I'll just be assuming that these two bodies are bonded together as well as these two bodies. So I'll just add some bonded contact and then use my named selections because it's a bit easier in this case, and start with my armrest right inner, which are those four faces, and select my armrest right outer. which are those ones. Again, very important to orientate the contact directions. Okay, then let me just duplicate this. So there's a lot of duplication that you can use as well. Just going to repeat this for the left side. Left inner. And left outer. Then just repeating that for top piece. So right inner and the armrest itself. Right armrest. Here we go. It's the one at the top. So those two will be bonded there. And then let me duplicate this one. Left inner, left armrest. Okay, awesome. So that covers the armrest contact. Then we just need to define the contacts here from the support to the back. So here is a connection that I also just want to define. So I'm going to assume that there's a screw or something in here that keeps this body fixed relative to this one. So I'm just going to add a fixed joint and then use the faces to define it to these edges of plates. Okay. Then for this, I'm not entirely sure what's happening here, but in this case, I'm also just going to bond this surface to this rod. So if you want to capture more detail, you could always do a submodel in an area like this, but this is something we'll cover next week. Okay, so let me just add another bonded contact here. I'm just going to select this face and this face. So it's a bit hidden, so I'm going to use the selection plane tool to select the right face. There we go. Select the correct one. And I can see that my shell's not orientated correctly, so I'm just changing it to face to the bottom. Okay. Then over here, we just have another fixed joint. So that's quite quick, body to body, fixed joint. That's the face filter selected. Apply that pin to these two surfaces. Okay, cool. And then finally, just the bonded contact here at the back. Okay, so in this case, it doesn't really matter. I'll just use these faces. Okay, so that one's orientated correctly. And duplicate this one to do the other side. Apply, change that to bottom. Okay, and then just do that again for the top side. So this face is selected and this face. Okay, and duplicate again. We have this face and this face. Cool. Let's change the orientation. Okay, cool. So those are our contacts before we add the beam connections. So there we go. I think there's an additional contact that I've left out. I would just like to define a contact between this body and perhaps this bottom. I have defined a revolute joint, so it should keep it in position, but let's just do it for in case. Okay, so I'm just going to add a frictional contact. Apply. There we go. Okay, cool. Then I'd also just, I need to define the very last thing, perhaps maybe a bonded contact between this bottom edge here, which I'll make target. And then usually when I'm going to scope an edge now, so usually when you scope an edge to a face, it's advised to scope the edge as the contact. In fact, I think if you do it the other way around, then Mechanical gives you a question mark. So if you do ever scope a surface edge to another edge that in a normal direction, then just ensure that you scope the edge to the contact side. Okay, cool. So what I want to do now is just show you how I typically review my contacts. So as you can see, there are a lot of contacts. So then I'll usually just select my frictional contacts and change the frictional coefficient. In this case, I'll just use a arbitrary value of 0.5. Okay. Now I'd like to use the contact tool. So this you access from connections, right-click, insert contact tool. And I would like to review all of my contacts, so I have them included here. Okay, then 3 things that you can look at is the status. So that will tell you if it's sticking or sliding or whatever. Then also the penetration and the gap. So if you have excessive penetration, there might be some excessive stresses there in the end that shouldn't actually be there. And if you have a gap that is too big, then you might have contact statuses initially that are open, or maybe even surfaces that don't see each other because the pinball radius is a bit small. So let me just generate initial contact results. So what this will do is just give me a graphic representation of the contacts that I've defined, of the initial contacts that I've defined. So even when we do a static structural analysis, contacts can still have statuses between open and closed. And that's why your frictional contacts and or any sliding contacts and things like that is status dependent, which makes it a nonlinear analysis. So, okay, we can actually review. So if I click on status, you can see here that all the bonded contacts that I've defined will be highlighted in this orange reddish color, and the sliding will be in lighter orange, and then near will be in yellow. So this just kind of helps you to visually make sure that you've captured everything that you need to. And I'd just like to point out that sometimes you can see here it is sticking. It's because the software works with a contact stiffness. So essentially it kind of just distinguishes between contacts in that way. Okay, so I'm just going to now then apply my beam connections, and then we are ready to just apply the boundary conditions or the constraints to the model and look at the results. Okay, so for the beam connections, I want to show you how to use the object generator to generate beam connections. So in this case, I have plates that are actually overlapping. So a bolt will go from the inner edge over here. Maybe it's screwed in up to this plate, and then, oh, not this one, sorry. This base plate, and then up to this back supporting plate. So I've made this mistake as well. So what people will then do is scope a beam connection from this outer edge, or if there's a washer face, you can also do that, to the inner one without taking into consideration this middle edge. So in this case, the middle edge will still be free to move around because your beam connection doesn't have any nodes between these 2 points. So in this case, I'm going to approximate this connection as a beam connection from the base to the base plate, and then from the base plate to the other connector plates. Okay, so let me start from the base plate onwards, just making sure my connections branch is highlighted, and then I'll select this edge and then say insert beam. Okay, so the diameter of this hole is 15 mils, so I'll change this to 7.5 mils. Okay, so that captures the beam connection over there. So I'd like to repeat this for this side. So I've created named selections for the associated edges that I'd like to use. So I'm just going to highlight this tree item, go to the automation tab, and then click on the object generator. So the object generator is something that will automate a action that is, or that would be repetitive. So in this case, it would be to repeat the process for the other side. So in this case, I can simply use my name selections to automate this process. So I have called this the 15mm base, so that's the inner edges, and the mobile side will be the 15mm base plate for arms. Okay, so then what I'd like to do now is just insert the distance between the centroids of the objects, which I can find here in the details of the beam connection. So in this case, it is 10.75. So I'm going to just insert between 10 and 11, and then select each entity and select generate. No, that's fine. Okay, go. So I've repeated the process on that side. And now I just need to define the beam from this plate to this plate. So just going to repeat the process, insert beam, make it 7. And just use the object generator again. So in this case, my reference will be the 15mm base plate for arms and the 15mm arm plates. And in this case, it's a very short beam. It's only about 5.5. So I'm going to use 6 and then just click generate. Yes, it's fine. Okay. And then I've repeated the process on the other side. So that is how I usually kind of approximate these kind of connections. I'm not going to repeat it for all of these connections now, but you'd still need to define a beam connection between these two edges, as well as on that side, and then of course here at the back as well. So I do have all of those name selections, but to save time, I'm not going to do those now because I have a solved solution already. Okay. Now what I want to do is just add my loading. So when I have a point mass, like in this case, it's important to remember to just include your standard Earth gravity. In this case, I'd want it in the Y direction, so I can just change that. Okay, so this will now take into consideration the weights of all the objects for which you have a density defined, as well as any point masses defined. Okay, then I'd also like to just include the supports. So in this case, it's quite simple. I'll just select it's simply supported, and then select my vertex filter tool, and then just control select all of these vertices. Click apply. Okay, so they're simply supported now. My standard Earth gravity is defined, and I think that is that. So in this case, the loading conditions are quite simple, but it's because I'm more focused on how to kind of use the interface to correctly apply these kind of loads. So, okay, I think that is it. Then if you want to just kind of have a summary of your analysis, you can click on the static structural branch and it will show you all the loads that you have applied here. Okay, so I'm quickly going to run through how I would just do the harmonic response analysis, and then we'll start with the post-processing. Okay, so if I go back to my workbench, just to show you, so the solution is linked to the setup of this model, and similarly between the modal and the harmonic response. So this means the modal analysis that I will be conducting here is a pre-stress modal analysis, as I've mentioned, and I'll be calculating the harmonic response based on these mode shapes. And then, as I've mentioned, I'll use a solution combination to combine the two. Okay, so in the modal analysis, there's not much really to do. You can just maybe look at the analysis settings, and if you want to limit the frequency range that you search for your natural frequencies, or not search for, but solves for, You can change that. In this case, I'm just going to leave it as the default of 6 modes to find. So it will go and solve for the first 6 eigen vectors or values. Okay, so I'll just then right click and hit solve for it to solve the modal analysis, and under the solution branch, you'll see all the mode shapes listed, which I'll show you very shortly. Then in your harmonic response analysis, here is where I'd like to apply my rocking back and forth motions. So in this case, I'm just going to insert a force, and I have a named selection for this as well. I think it's just the harmonic load. So this will be applied in this direction. So just before I carry on with scoping this load, I'd just like to point out that harmonic response is a linear dynamic analysis. So I'm going to use the mode superposition method that kind of just takes the mode shapes of the modal analysis and solves the linear equations as well to determine the harmonic response. But usually it's only at one frequency. So in your analysis settings, you need to set the range of the frequencies that you want harmonic response for. So we have half hertz that we'll be using. So I'm going to just run my analysis from 0 to 1 hertz. And in this case, the solution intervals will then give me the harmonic response because there's 10 at 0.1, 0.2, etc., up to 1 hertz. You can increase this as necessary, depending on where and how many points of frequencies that you want to evaluate your harmonic response to. In this case, we'll probably just evaluate it at half hertz to see what's happening. But yeah, so that's just something important to mention. So if you insert a force or any load, then it will always be, all the loads and all the forces will be at the same harmonic frequency, but they can be out of phase with each other. So just something important to remember. Okay, so I'll be applying this force using components in the Z direction. I'm just going to assume it's about 20 kilograms of rocking back and forth. Actually, I want to change this to tabular data, so you can also do this. If you want to define any, there we go, any loads that are frequency specific, then you can also input it here. So let's just, for example, say here that at a half hertz, this is 200 newtons. So this is our harmonic load. Okay, you can also input more frequencies if need be, but I'm just going to keep it for as that is now. And then just another really important thing to mention with your harmonic response is that usually you would be running a damped analysis because that's representative of your boundary conditions probably. And in the cases of running an undamped solution, you might see some very high excitations close to the natural frequencies of the body. So when I did my analysis, I just applied an arbitrary damping coefficient value of 0.01, I think, just to kind of minimize those values at the natural frequencies. So this you can do under damping controls if necessary. Okay, then another option is cluster results. So when you put this on, it will evaluate the harmonic response to frequencies close to the natural frequencies and not at the set intervals that you have specified. So, okay, I think when we look at the results, it will make a bit more sense. So let's actually start doing that now. Okay, here we go. Let me go to my solved solution. So I'm just going to close the other one. It's not really necessary, but it's just so I don't get confused between the two. Okay, let me open the results. Okay, so what I'll be doing now is I'll just be plotting some standard deformation and stress plots, and as well as the harmonic response to the applied load, and then maybe just look at some fatigue of some of the support structures. Okay, then also just like to point out for this static structural analysis, the only analysis setting I changed was large deflection. I switched that to on, and that is just to take into consideration any stiffness changes due to excessive deformation. So, okay, here we go. We have our applied loads, as you have seen in the other analysis. So I'm just going to insert my plots. We'll look at total deformation. We'll look at the maximum equivalent stress. So in this case, the total deformation I want to see everything for, but maybe the equivalent stress, I'm only really concerned with the surface bodies. So I'm going to hide all the solid bodies, and then maybe just select all and apply that to the stress plots. Okay, evaluate all results. Oh, this is meant to be just show bodies. There we go. Okay, so here we can see, let me just change the display back to thick shells and beams. The response of the chair upon sitting. So let me just also turn off elements, no wireframe. There we go. Okay, if I want to animate this, I can just go to the Home tab, the Result tab, click on Graph, press play. Okay, so here we can see exactly what's happening when the human sits on the chair. Okay, there we go. And also plot directional deformation plots that will give you X, Y, or Z specific results, but the total deformation is just the root mean square value of all of those together to get kind of a global idea of what you're doing. Okay, then there's equivalent stress plots. I can see there's highly localized stresses over here where the beams are connected to this bottom shell body, as well as I think at the end of where the full load is applied, this top plate is also starting to see some significant stresses. Okay, this localized stress over here is very high. It's estimated as approximately 1 gigapascal. So this will probably be due to the beam being connected straight to the surface body with shear topology. So in fact, there is a point load in this case that is causing this stress singularity. So this is also a good place where you can run a submodel to kind of capture the connection detail in this case to get more realistic stresses if you want to look at your local behavior. Okay, so here we go. This is our stress plot. Most components are fine except for these bottom surfaces. Can also scope it to the full chair, but I don't think the seats saw much either. I just want to perhaps look at this back plate over here. Okay, still very low. Okay, so this is just something interesting to take note of. So during the static structural, these components here are fine. It's mainly these bottom plates over here and the beam connections there at the bottom. Okay, then after that, we ran our modal solution to find the first 6 natural frequencies together with the displacement. So this is the first natural frequency of this chair at 0.28 hertz, approximately 0.3 hertz. And there are some interesting deformation plots to look at just to kind of visualize the response. Okay, and then finally looking at the harmonic response analysis. So there's a variety of interesting results that you can request here. I'm going to start with just the deformation as well and the stress. So this will be due to the harmonic load, and it will be shown at the maximum frequency that I've specified in the analysis settings of 1 hertz, but I'll show you how to extract results for other frequencies Okay, so let me just evaluate these results quickly. Okay, here we go. So at 1 Hertz, the response of the chair will look something like this. Okay, but if I wanted to see maybe what's happening at 0.5 Hertz, where I'll be applying the load, I can go to a close-ish results and maybe just, oops, why is it doing that? Just right-click, double right-click. There we go. Oh, it just hides it. Wait. Double click. I've struggled with this before. Oh. Let me just maybe try with the equivalent stress plot. Okay. There we go. Nope. Don't know if my mouse is not working properly. That could be it. Anyways, when we look at the equivalent stress plots of the harmonic response, in this case now you can see that this backplate is actually seeing a lot more stress than with the static structural. Let me actually scope just this plate. I actually just want to see what's happening. Evaluate all results. There we go. Okay, so I can see this plate is actually seeing a lot of load due to this rocking back and forth motion. Okay, let's try again. See if I can get a result here. Oops, misclicking. Okay. Otherwise, you can go to your graph and you can also say extract this result. So I think it is the 21st-ish. Okay. So retrieve this result is an alternative. Okay. So it's just busy retrieving that. And then you can see now that the frequency in this plot has updated to 0.75 Hertz, for which I can now see the response. Okay, a bit slower. Okay, cool. Then just something interesting that I wanted to show you is that if you were to look at the harmonic response of this chair close to its first natural frequency of 0.2876, you'll get ridiculously high stresses. So let me just show you. Actually, I can just quickly go here and look at which one it was. It clustered the results around the first natural frequency, as I've mentioned, so I can select any of these really. Let's select number 7. Okay, so this should be quite high. Yes, 400. Oh, yeah. So as you can see, the deflection that they give here is 400 millimeters. So obviously that is excessively high, and this is probably due to the damping not being correctly applied. So I don't have that information, unfortunately. So that's why damping or doing analysis with damping included is a bit of a challenge. It's more a challenge to get that information, if that makes sense. But in this case, I did add the little bit of damping just to reduce the stresses. Before I did that, without damping, I think the stress at this frequency was something like, I don't know, 90 gigapascals or something ridiculous. So the harmonic response close to the natural frequency is excessive. Then you can also request specific frequency response plots if you were to need that. So I'm going to plot a stress response plot of a vertex. I think I'll select this one, which was the worst. And then this will also just give you the boat plots of the response of the system. So that is quite cool. In this case, you can see the amplitude and the phase angle to just kind of see what the lag is of the response behind the applied load. So that is quite nice. Then if I wanted to look at fatigue, then it's important to note that with the material data you need to ensure that the bodies that you're looking for do have SN curves available. So in this case, the aluminium alloy that I have selected does have its SN curve over here, as well as the structural steel. I don't think the ABS has one, no. Okay, so I'm going to also scope my harmonic response to my support structure, the fatigue tool. So that's what I'm going to do next. So just right click there and then insert a fatigue tool. I'm going to evaluate the life and the damage of not all the bodies, but let's perhaps, I should have created a name selection for this. I did, wait, let's see. Okay, but I think, I don't know, I think it's only selecting the faces. So I prefer to select the bodies. Apologies for that. Yeah, it's only the faces. Okay, so I'm just going to select the bodies that I'm interested in. Actually, just maybe these. Okay. Oops. Awesome. Okay, cool. So let's see how long this will last at 0.5 hertz. So when you do run the fatigue tool, it's just important to insert the frequency at which you'd want the response. So in this case, I'm going to say 0.5 hertz, which it'll probably interpolate for. And then I'll say evaluate all results. Okay, oh, it actually plotted all the bodies for this first one. So as you can see, the results for the cushions are not accurate because there are actually no SN curves defined. Let me just add another life plot. I didn't do it right. Damage 13 bodies. Oh, I can't select them again. Okay, sorry about this. I just quickly want to select them again. Sorry about that. My name selection is not working. There we go. All the exact same ones that I just used, but doesn't matter. Okay. Okay, cool. There we go. I've selected 3 more bodies this time. Okay, cool. Let's evaluate. Okay, so here we can see the expected life of this assembly. Not very long, so the minimum situated at this vertex, I think. Oh no, actually at this connection as well, where we had the high stresses. Okay, so this is what we get. So obviously the expected life is almost 0, so it will snap off right there at the very beginning. Okay, well, if I wanted to, let's look at this backplate as well, since it's seeing quite an interesting deflection load. I want to actually see what the expected life is as well of maybe just this body. Okay, cool. Evaluate all results. Life 3. Yeah, there we go. So this is quite a nice plot where you can see how the cyclic load is affecting this plate. So that's quite cool. Okay, so we have some parts that will last forever, and then we have some parts that will fail almost instantly, and then we have this part that will last approximately 1 million seconds, which is unfortunately not sufficient for our design specifications. So yeah, I think this covers most of the things that I wanted to discuss and show you. I hope that I've covered most of the stuff that you had questions about or anything that you were wondering about. Yeah, I think that's it. So next week, we'll be looking at probably a submodel of one of these high stress regions. And we'll also be looking at some topology optimization. So that's going to be interesting as well. We might be making some changes to the geometry, but all in all, again, it's just for demonstration purposes. And yeah, I hope this was useful to you. Okay, Laura, that is everything from my side. Yeah, I covered everything that I needed to.
Okay, thanks a lot,
No
Johnny.
problem.
I think everybody, yeah, be careful on the seat that you're sitting, eh? Watch out.
Don't rock it back and forth.
So there's a question in the chat from Louis Rousseau. Does the
Okay.
fatigue tool also take mid-ranges stresses into account when calculating life? I assume the mid-range stress will be due to the weight of the person on the chair.
The mid-weight, yes. So the fatigue tool, the fatigue tool is based on the harmonic response, and the harmonic response does take the point mass into consideration when and only when there's acceleration applied to it. So in this case, there's gravity. So I think it is included, yes. So if not, then oh, I actually still wanted to show the solution combination, Laura. So that is when you'll do a solution combination. So if you want to kind of combine the stresses from the two, you'll do that. So it's quite easy. I'm still sharing my screen. Let me just show you. So on the model, you just select insert solution combination. So what I'll be doing now is I'll be combining the stresses from both load cases into one. So because I have my static structural analysis where I determined those stresses, and I had a pre-stress modal analysis which calculated the pre-stress mode shapes, and then I wanted to see the harmonic response of that to only the cyclic load, but now to combine the two, you just simply do this. So right click and include a solution combination. Then in this case, I'm just going to add, not a combination. I want to add a base case. So, okay, let me just choose my static structural first and add a base case, and then choose my harmonic analysis. So the base case is just the type of analysis that you'd like to select. And yeah, that's it. And then I think you just need to insert a plot. Let's just quickly do that. Stress. And then just quickly evaluate the results. It's not doing it. Solve. Okay, it's not working. Maybe I need to. Sorry, okay, I made a mistake, but what this should give you is just the combined stress plots of the two. So that's how you can take both cases into consideration, essentially. Yeah, so let me just see what's happening over here.
Okay, but thanks. I think that answers the question, definitely.
Yeah, I just need to insert a 1. So I hope that answers the question. Sorry, here the combination, I just needed to insert 1 as a factor. Otherwise, it's just 0. There we go. Okay.
Louis, you can unmute yourself if you want to, just to confirm that we've answered your question. Or just in the chat.
Yeah, so what I'm showing here now is the combined solution. So if I look at the equivalent stress now, in this case, it will show the combined solution of the stresses caused by the cyclic load as well as the static load. So it's just, let's put 280 in just to get a better representation. There we go. So you can see the failure occurring here due to the static load as well as the cyclic loading over there. Okay. Are there any other questions from anyone? It doesn't look like it.
Well, let's just check. There's one hand.
Okay.
Okay. Question. Tapilu, yes? You can unmute yourself and ask.
Unfortunately, I don't know what happened to my site. I can't type on the chat.
Oh no.
Yeah. Seeing that you were able to combine or include harmonic analysis on this study, I believe you can draw up a mathematical model of a control system to see what can be adjusted or maybe modify to reduce the noise that the chair will be making as one apply that harmonic load. I believe so.
Okay. Okay, so is that another way to do that, Sopelo?
Yeah, I saw you did display the phase angle and of the and the frequency. So by seeing that, I've realized that you can actually also apply control system on how can you design the chair to maybe make less noise as one applies the harmonic what you call motion. Thank you.
Yeah, no, you're right. That's cool. Thanks, Sopelo.
Thanks for that. Any other questions? Well, I think that's it then for our session 2 of the FEA series. So thank you very much, everybody, for attending. Enjoy the rest of your weekend. For those who are in Cape Town, I would assume enjoy the cold weather.